Volume of distribution. The apparent volume of distribution, VD, can be thought of as the fluid volume that is required to contain the entire drug in the body at the same concentration measured in the plasma. It is calculated by dividing the dose that ultimately gets into the systemic circulation by the plasma concentration at time zero, C0. Although the volume of distribution has no physiologic or physical basis, it can be useful to compare the distribution of a drug with the volumes of the water compartments in the body. Distribution into the water compartments in the body. Once a drug enters the body, from whatever route of administration, it has the potential to distribute into any one of three functionally distinct compartments of body water, or to become sequestered in a cellular site. Plasma compartment. If a drug has a very large molecular weight or binds extensively to plasma proteins, it is too large to move out through the endothelial slit junctions of the capillaries, and thus is effectively trapped within the plasma vascular compartment. As a consequence, the drug distributes in a volume, the plasma, that is about 6% of the body weight, or in a 70 kilogram individual, about 4 liters of body fluid. Heparin shows this type of distribution. Extracellular fluid. If a drug has a low molecular weight but is hydrophilic, it can move through the endothelial slit junctions of the capillaries into the interstitial fluid. However, hydrophilic drugs cannot move across the lipid membranes of cells to enter the water phase inside the cell. Therefore, these drugs distribute into a volume that is the sum of the plasma water and the interstitial fluid, which together constitute the extracellular fluid. This is about 20% of the body weight, or about 14 liters in a 70 kilogram individual. Aminoglycoside antibiotics show this type of distribution. Total body water. If a drug has a low molecular weight and is hydrophobic, not only can it move into the interstitium through the slit junctions, but it can also move through the cell membranes into the intracellular fluid. The drug, therefore, distributes into a volume of about 60% of body weight, or about 42 liters in a 70 kilogram individual. Ethanol exhibits this apparent volume of distribution. Note the difference. Apparent volume of distribution. A drug rarely associates exclusively with only one of the water compartments of the body. Instead, the vast majority of drugs distribute into several compartments, often avidly binding cellular components such as lipids, abundant in adipocytes and cell membranes, proteins, abundant in plasma and within cells, and nucleic acids, abundant in the nuclei of cells. Therefore, the volume into which drugs distribute is called the apparent volume of distribution, or VD. VD is a useful pharmacokinetic parameter for calculating a drug's loading dose. Determination of the volume of distribution. The fact that drug clearance is usually a first-order process allows calculation of VD. First order means that a constant fraction of the drug is eliminated per unit of time. This process can be most easily analyzed by plotting the log of the plasma drug concentration, Cp, versus time. The concentration of drug in the plasma can be extrapolated back to time zero, the time of injection, on the y-axis to determine C0, which is the concentration of drugs that would have been achieved if the distribution phase had occurred instantly. This allows calculation of VD by dividing dose by C0. For example, if 10 milligrams of drug are injected into a patient and the plasma concentration is extrapolated back to time zero, the concentration is C0, which equals 1 milligram per liter, and then VD equals 10 milligrams per 1 milligram per liter. It equals 10 liters. Effect of the volume of distribution on drug half-life. A large VD has an important influence on the half-life of a drug because drug elimination depends on the amount of drug delivered to the liver or kidney or other organs where metabolism occurs per unit of time. Delivery of drug to the organs of elimination depends not only on blood flow, but also on the fraction of the drug in the plasma. If the VD for a drug is large, most of the drug is in the extraplasmic space and is unavailable to the excretory organs. Therefore, any factor that increases VD can lead to an increase in the half-life and extend the duration of action of the drug. Note that an exceptionally large volume of distribution indicates considerable sequestration of the drug in some tissues or compartments. Let's have some quizzes. The following graph shows the elimination time course obtained after giving a 400 milligram dose of a drug given by either IV or oral routes. From the data shown, the volume of distribution of the drug is. The answer is 50 liters. VD equals dose divided by C0. So 400 milligrams are divided by 8 milligrams per liter, and the result is 50 liters. A 70-kilogram man with severe burns arrives in the emergency department and requires IV morphine to treat his pain. The VD for morphine is 200 liters. What IV loading dose do you need to give to rapidly achieve a therapeutic level of 60 nanograms per milliliter and relieve his pain? The answer is 12 milligrams. VD equals dose divided by C0. So dose equals VD multiplied by C0. First, we should convert the units of the concentration from nanogram per milliliter to milligram per liter. 1 nanogram equals 10 to the negative 6 power milligram, and 1 milliliter equals 10 to the negative 3rd power liter. So we will multiply 60 by 10 to the negative 6 power and divide them by 10 to the negative 3rd power to become 0.06 milligram per liter. Then the dose will be calculated in this way: 0.06 multiplied by 200, and the result is 12 milligrams. For studying pharmacological science, go to the link in the description box below this video or in the comments section. Thanks for watching and happy studies.